Hi, I'm Sudhakar Kakirani. In today's video, we are going to understand microservices architecture, which is widely used in modern software systems, retail platforms, and e-commerce applications. In earlier days, most applications were built using monolithic architecture, where the entire application was developed as a single large program. But as systems grew bigger, maintaining them became very difficult. To solve this problem, the microservice architecture was introduced. In microservice architecture, the application is divided into small independent services. Each service performs a single specific business function. Let me explain the key concepts in microservices. Let us understand microservices. For example, in a retail or e-commerce system, we can have services like user service, product service, order service, inventory service, payment service, notification service. Each service runs independently and communicate with other services through APIs or messaging systems. Microservices provide several advantages. Development is fast. We can deploy easily. Its scalable architecture depends on the business growth. We can scale it easily. Fault isolation isolates the fault service. For example, if the payment service fails, the product service can still work. This makes the system more reliable and scalable. Many large companies like Amazon, Netflix, Uber are using microservice architecture. Next key concept is API gateway. The usage of API gateway in microservice architecture is when many microservices exist. Clients should not call each service directly. Instead, all requests go through a single entry point called API gateway. An API gateway acts as a central door for all client requests. Mobile apps, web apps, and POS systems send requests to the gateway. The gateway routes the request to the appropriate microservices. Example, in this diagram, the client sends a request which first reaches the API gateway. The API gateway then routes the request to the appropriate microservice. Once the request reaches the service, the business logic is executed, and as part of that process, the service interacts with its respective database. For example, when a client sends a user service request to the API gateway, the gateway forwards that request to the user service. The user service then executes its business logic and connects to the user service database as needed. After the execution is completed, the response is sent back to the API gateway and finally returned to the client, which is a front-end application. Responsibilities of API gateway are request routing, routes the request to the appropriate service. Authentication authorization. This means verifying valid credentials and checking whether the user has permission to access a particular service. If valid, the request is allowed. Otherwise, it is rejected and a response is sent back. Rate limiting restricts the number of incoming requests per client within a specific time frame. This helps prevent service overloading, traffic spikes, and ensure system reliability. Load balancing distributes incoming traffic across multiple service instances to ensure high availability, low latency, and fault tolerance. Logging and monitoring monitors the system and provides end-to-end tracing of requests and logs for better visibility and troubleshooting. Finally, the conclusion is the API gateway simplifies communication between clients and microservices and improves security, scalability, and maintainability of systems. Next key concept is microservices communications through REST and messaging system. REST communication. Let us first understand REST communication in microservices. In REST, one microservice communicates with another using HTTP APIs. For example, when the order service needs to process payment, it sends an HTTP request to the payment service. The request is usually sent in JSON format, and the response also comes in the JSON format. This is called synchronous communication because the sender waits for the response. REST communication is simple, easy to implement, it's widely used, but it has one limitation. If the target service is slow or down, the calling service is also affected. Messaging systems. Now let us understand messaging systems. In this approach, service communicate using messages instead of direct calls. For example, the order service does not directly call the payment service. Instead, it sends a message to a message queue. This message is then processed by the payment service. This is called synchronous communication because the sender does not wait for a response. Popular messaging tools include RabbitMQ, Apache Kafka, NATS, Apache Pulsar. Here we use patterns like a publish and subscribe, message queues. Messaging system provides better scalability, loose coupling, higher reliability. Even if one service is down, messages can still be processed later. Now, tools and technologies. Let us look at some important tools and technologies used in microservices communication. Postman. It's used for testing APIs. Swagger. Used for API documentation and design. gRPC, a high performance communication protocol faster than REST. Protocol buffers. Used with gRPC for efficient data serialization. GraphQL allows clients to request only the required data. These tools help developers to build APIs, test services, improve performance, maintain documentation. So, in summary, REST is simple and synchronous. Messaging system are scalable and asynchronous. And tools like Postman, Swagger, and gRPC, they help us build efficient microservices systems. Next key topic is Docker and microservices. Docker is a platform used to package applications into containers. A container includes application code, dependencies, runtime environment. This ensures that the application runs consistently across different environments. Key Docker components are Docker images, blueprint of the application, Docker containers, running instances of images, Docker engine, it's a runtime to manage containers, Docker compose, it's used to manage multiple containers. Microservices with Docker. In microservices architecture, each service is developed and deployed independently using Docker. Each microservice runs inside its own container. For example, user service runs in one container, order service runs in another container, payment service in another container, and so on. Each service also connects to its own database. How they work? Docker helps microservices by providing isolation between services, enabling independent deployment, makes scaling easier, ensuring consistency across environments. All services communicate through APIs. Deploy anywhere. One of the biggest advantages of Docker is build once, run anywhere. You can run Docker containers on local machines, cloud platforms, Kubernetes clusters. Benefit side, using Docker with microservices provides faster deployment, better scalability, easy maintenance, high reliability. In summary, microservices divide the application into small services. Docker packages each service into containers, and together they create scalable, flexible, and modern systems. The next key topic is Kubernetes for microservices. Kubernetes is a container orchestration system. It is used to manage, deploy, and scale Docker containers automatically. When we have many microservices running in containers, Kubernetes helps us handle them efficiently. Key components. Let us understand the key components of Kubernetes. Pods. A pod is the smallest unit in Kubernetes. Each microservice runs inside a pod. Nodes are machines where pods are deployed. Deployments manage how many instances of a service should run. Services provides networking and allow communication between pods. Microservices in Kubernetes. In a microservice architecture, each service runs inside a container. Each container runs inside a pod. Kubernetes manages all these pods. For example, user service is a microservice, runs inside a container, and this container runs inside a pod, and this pod runs under the Kubernetes. Each service can scale independently. Key features. Kubernetes provides powerful features like auto scaling, automatically increases or decreases pods based on traffic. Load balancing, distributes traffic across multiple pods. Self-healing, if a pod fails, Kubernetes automatically restarts it. Service discovery, services can easily find and communicate with each other. Rolling updates, deploy new versions without downtime. How it works? Kubernetes continuously monitors the system. If traffic increases, it creates more pods. If a pod fails, it replaces it automatically. This ensures the system is always available and reliable. Benefits. Using Kubernetes with microservices provides high availability, scalability, fault tolerance, easy deployment, better resource management. In summary, Docker creates containers. Kubernetes manages those containers. Together, they power modern microservice applications. Now, let me give the final conclusion. Microservices are suitable for when large complex applications with evolving requirements, and if applications requiring high scalability and independent deployments, and when you developing projects teams needs the flexibility to use different technologies. In these situations, we can use microservices. Thank you. Have a good day.